right, everyone. So now we're going to be moving on to the topic of the analysis of variance test. This is going to be an analysis that is a bit more functional, a bit more useful than your basic t-test, but we're still living in the realm of group differences based analyses. So this is going to be split up into several different parts because it is a topic that has a few different aspects to it. So let's just jump right in. So variance begins by sort of building on your basic t-test. The idea is that a t-test is a simplified sort of an analysis of variance when you're just comparing two groups and you're evaluating whether or not the two groups differ in the mean of some outcome. Whether it's a related samples t-test or an independent samples t-test, there's going to be two groups present. The analysis of variance, or ANOVA, is going to be the group differences correlate analysis in which there are three or more groups. There can actually be as many groups as you want. But if you're dealing with any more than two groups, you need to be living in the analysis of variance realm of analyses. So the idea, as with t-tests, is that there's several different research designs that might yield three or more groups. So for example, individuals within your study might be exposed to three different conditions of your independent variable. So again, the repeated measures design that we saw in the related samples t-test, that could be translated into analysis of variance. It's just that if you have more than two conditions, that is to say three or more, you would need to use the ANOVA instead. Or if you have your participants selected into three distinct groups, and each individual participant is only exposed to one of the three treatment conditions. Again, the fact that there's three groups or three levels necessitates the usage of your ANOVA. There's levels of advanced research designs that will determine which type of ANOVA you can use. So as with many sorts of analyses, there's the simplest version, and if you have more intricate research designs or more intricate or complex hypotheses, you might need to use a more advanced version of the same analysis. So the most basic version of your ANOVA is what we call a one-way ANOVA. This just means that it's an analysis of variance in which we are evaluating a single independent variable. Recall, as with t-test, that the idea is that you have a single independent variable, but since it's a variable, it must have different levels within it. So a single variable with at least three levels within it. So no matter how many levels exist within your one independent variable, it could be as many as you want, you use a one-way ANOVA. A two-way ANOVA, on the other hand, is when there are two separate independent variables, or IVs, at play. So this is going to be a more complex version of ANOVA. So we're going to start more simple today with your one-way ANOVA. It's still, at its most basic, a bit more of a complex analysis than a t-test, for sure. But it's also more functional in that there's more things that you can do. You can evaluate more complex hypotheses. Okay? So again, if you have two independent variables, you do a two-way ANOVA. Now, likewise, as many levels can exist within each of those IVs, but the idea is that the distinction between one-way and two-way ANOVA is one versus two independent variables. So again, we're going to start with the one-way ANOVA today. Okay, so let's dig into the theoretical reasoning and the logical underpinnings of the ANOVA before we get to any actual calculations. So if we suppose that a independent variable, that we have a certain number of levels or conditions with it that we'll notate as K, K standing for the number of levels, the basic question we're asking is whether or not there's an effect of our independent variable. Let's say our independent variable is treatment, and the treatment levels are active treatment versus minimized treatment versus control. The idea is, are there differences between those groups? As with the t-test, you can have different designs that would still be this most basic form of ANOVA. So you could have a between subjects design or within subjects design. The basic distinction is the same as what we learned with the t-test. The between subjects design is going to have your participants randomly assigned for the best solid research validity, randomly assigned subjects to your various conditions. So if you have a treatment one group and a treatment two, that maybe they're receiving different versions of a therapy, and then a control group, the idea is that you want to randomly assign those participants to each of those three different groups. So this is like an independent samples t-test because each group will only experience one of those levels or conditions. You could have a within subjects design with your one-way ANOVA. Again, a single independent variable. The idea, though, is that if you have an independent variable that has 3 or more levels within it, the idea is that your participants would walk through each one of those conditions in a series of exposures. So this is like a related samples or repeated measures t-test. So the idea would be all participants in, let's say, the example I was just using, go through a control condition time period where they receive no treatment for a while. Then they move on to a low-level treatment. And then after another period of time has passed, they move on to a high treatment condition. So the idea is that, again, your participants will all see every level of your independent variable. So we're going to walk through an example. Again, we're not going to get to the computation just yet. I want to make sure we understand the logic of the ANOVA before we see any of the computations. So this is going to be the example we're starting with. Suppose we're interested in whether different situations produce different amounts of stress. We take a group of 15 subjects and measure their stress in 3 situations. 5 subjects are tested just after a vacation. 5 are tested mid-semester. 5 are tested during final exam week. We measure the blood level of a hormone that is known to be related to stress. So again, there is only a single independent variable here. It's time period, but it has 3 different levels. We've got people from the vacation group, the mid-semester group, and the finals group. So this would be a case in which we want to do our one-way ANOVA. Make sure that you're understanding that there is a distinction between the independent variable and the dependent variable. So the independent variable is going to be the grouping variable. The dependent variable is going to be a distinct outcome. So your data would start off looking a little bit something like this. Like I said, I want to ease into this, so we're not going to look at the numbers just yet. We want to spend some time building a solid base understanding of the logic of the ANOVA. Right here would be your basic data breakdown. You've got your 5 individuals in level A1, your 5 individuals in level A2, and your 5 individuals in level A3. So you're going to want to keep your different groups straight so you can evaluate the differences between the groups. Again, this is a group differences based analysis. So the idea is that the vacation group is going to have a mean level of stress, likewise with the semester group, likewise with the exam group. Okay, there's an overall mean between the 3 groups overall, but we want to understand basically whether or not those 3 different means are different. So you might be asking yourself, why couldn't we just do t-tests? Couldn't we just run a series of t-tests in which we compare 2 groups together and we just proceed with all possible combinations until we've compared all groups separately? Yes, you could do that, but there's a statistical problem that lies in doing multiple tests like that. The idea is you have your accumulated type 1 error rate. So each time you run an individual test, you have your standalone error rate, which typically we're only going to evaluate significance as being at the p equals 0.05 rate. If you do a series of similar tests over and over and over, you're basically going to have an overall what we call experiment-wise error rate. Given that we have 3 different chances to make that type 1 error, we have to combine the 5% error rate that we're taking in each of those individual analyses. So this overall error rate is actually inflated above and beyond the individual error rate in each of those single t-tests. There's a way to analyze your overall experiment wise error rate. You're not going to need to do this, but I'm just going to show you so you understand what this looks like. The idea is if you were to run a series of 3 separate t-tests, you can actually calculate what your new error rate would be. In this case, it would be an error rate of just about 15. So we don't want that. We don't want to inflate our likelihood of making an error, which is what running a series of tests after test after test does. The analysis of variance is basically going to control for this. By simultaneously evaluating all of the groups at once, the ANOVA is going to control for that experiment-wise error rate, and it's going to keep it at that p equals 0.05 level, no matter how many groups we have. Built into the computation of the ANOVA is a correction for the number of levels, and it makes sure to keep that error rate at p equals 0.05 where you want it. As with all of our inferential tests, some assumptions about the data should be evaluated to hold true before the test can reasonably be used and interpreted. One is that your outcome should be measured on an interval or ratio scale. Again, I'll reiterate that as opposed to the independent variable, which is a categorical variable in that it chunks people into groups, the DV is meant to be on an interval or ratio scale because the outcome is meant to be assessed by a mean level. So again, your independent variable in the example I just described would be time period. The dependent variable of stress would need to be evaluated and measured on that interval or ratio scale, and it must be a quantitative variable. The populations from which the samples are taken should be relatively normally distributed for each level of the IV. And as with the t-test, the variance within all of your levels should be roughly equal. So homogeneity of variance, again, means sameness of variance. You want your different groups to have roughly equal variance. All of the hypotheses within the context of ANOVA should be considered to be two-tailed tests, so you don't need to mess with this, am I running a one-tailed or a two-tailed test? Theoretically, all of your ANOVA hypotheses should be considered to be two-tailed tests. The null hypothesis that we'll be seeking evidence to contradict is that all of our samples, right, our 3 different groups, come from the same population, right? We're trying to find that there is some difference among all of our various groups. So the null hypothesis that we're trying to contradict is that all of the means will be equal. The alternative hypothesis is that you think at least one of the groups is different. At this point, you don't need to necessarily speculate which of the groups will be different, whether you think all 3 groups are going to be different, or whether just one differs from the other. The alternative hypothesis at the outset, when you do your ANOVA, should be at least one of the groups will be different. So this alternative hypothesis is that not all of the means are going to be equal. Again, you're not saying which are going to be different. You're not stating that they're all going to be different, just that at least one is not like the others. As its name suggests, the ANOVA, or analysis of variance, is all about variance. It's understanding variance. So again, I really want to break down the logical construction of this test for you because it is a slightly more advanced analysis, and understanding it at a theoretical level will help you a lot in the long run. Okay, so we've got our 3 groups in this example. We're measuring our participants on stress level at their 3 different time periods. The idea is that if we were to pool all of our subjects together, there's a total amount of variance among all our participants overall, and we want to be able to capture and understand how much variance there is overall. What the ANOVA is going to do is it's going to partition out sources of overall variance by breaking it up into its possible components. Right? There's a total amount of variance. There's 100% of the variance within our data. We need to understand how much there is, and we want to understand where the variance comes from. So the ANOVA is going to be analysis that breaks all of the variance within your data into its separate sources. So what do I mean by sources of variance? If we're dealing with a one-way ANOVA, meaning one independent variable, there's 2 sources that variance or differences between scores could come from. Scores might differ even when subjects are in the same experimental condition, right? So my 5 participants in the vacation condition are not all necessarily going to have the exact same stress level. They're going to vary a little bit within that one condition. This could be due to a multitude of factors, that people are different. People come into experimental research collection with individual differences in stress level. There could be measurement error. Maybe people are understanding my questions a little bit differently person to person. Basically, we don't really care about that. We inherently don't really care about this within treatment variance because what we're trying to figure out are whether the groups are different. So, individuals within the same group differing from each other, we naturally don't care about that. We're going to need to quantify it though, so we can partition it out. Scores, additionally, within all 15 of our participants may differ because they are from those different conditions. So this is what we call between treatments or between groups variance. This is the idea that the scores from the vacation people might be different from the mid-semester people and different from the finals people. That kind of variance we do care about because this is all about evaluating whether or not our groups are different. So if some of the variance can come from within groups error and some is coming from the different groups, the fact that people are taken from these different conditions, we want to understand and be able to quantify both of these sources of variance. So what we're going to need to do is we're going to need to assess how much of the total variance overall was due to this differing levels of the independent variable, this between treatment variance. So we're going to need to quantify both our within treatment variance and our between treatment variance to understand how much of the total variance was due to this between treatments source. Okay, so more on this within treatment variance, right? Some of the measure of variance in scores is going to be due to individual variability, measurement error, or the fact that people are just individuals and they're just different. We want to be able to quantify this error variance, notated here as error variance. The quantification of this error variance term is going to be called mean square within, or the error term, but that MS within notation, that's what we're going to be seeing in our equations. Okay, so again, variability in scores that occurs between levels of the independent variable, the stuff you actually care about, we're going to refer to this as our treatment variance, notated as treatment variance, otherwise called your mean square between term. So your estimate of just how much between treatment variance there is going to be quantified as this MS between. Okay, so MS between is a measurement of how much the means for the conditions differ, the stuff you care about. Okay, so again, we want to understand the logic of this test. So if we consider what it means for the null hypothesis to be true, all scores in all conditions are thought to come from the same population. So the mean in all your different groups should be equal. If we sample individual scores from the population, right, again, we're necessarily going to experience some variability in scores. The fact that some people are different means that there's going to be some measure of error variance whereby people are above or below where you might expect them to be. So the variability, that random variability that occurs when you're just taking different scores, is this error variance, this mean square within. So the idea, if you were to take a series of samples from different sizes from the population and you were to calculate means from each of your random samples, the samples are going to necessarily be different. Even if the people in the population are the same, your sample mean is not going to be the same time to time because you're taking different random groups. Okay, so the variability among the sample means, okay, and the treatment variance should be the same as your mean squares between. So again, think about what it would take for the null hypothesis to be true. All samples are thought to be taken from the same population. Any variability in your sample means is just due to this random sampling, and thus it's going to be the same as this error variance term, right? Again, the idea is that there's going to be some error variance within the groups that you definitely don't care about, but there's also going to be some between groups variance that you also don't care about, because it's just the fact that sample means are necessarily likely going to differ. Okay, but if this were to be the case, that the amount of error variance is all due to random sampling and variability within the groups, your mean square between and your mean square within will be estimating the same amount of variance. They're both just due to error variance. So if the null hypothesis is true, you're going to expect your mean square within term and your mean square between term to be roughly equal. The ratio, therefore, of mean square between to mean square within will be equal to 1, right? So again, this is what you don't want. This is if the null hypothesis is true and your groups don't truly differ. What you'll see in groups that are not truly different is that the mean square between is going to be capturing a similar amount of variance to your mean square within, and thus what you call your F ratio of your ratio mean square between to mean square within will be 1. So again, this is if the null hypothesis is true and the groups are not different from one another. If the null hypothesis is false, then the samples are not taken from the same population because they're truly different from one another. So if this is the case, that means that the variability in the sample means is due to some error variance, right? There's bound to be some error variance. You can't get away from it. But there's also going to be this extra added source of variance from the effect of the independent variable. That is to say, there is some variance due to these groups being truly different. This means that when you compute your mean square within term, it's going to include some of that error that naturally exists when you're sampling different groups, plus that additional variance due to the only source you actually really care about, the effect of the independent variable. If this is true, that means that same ratio of mean square between to mean square within will create a ratio whereby that obtained statistic is greater than 1. So anytime your F statistic that we're computing with this ratio is greater than 1, it means that there's some variance in your data due to the only source you care about, which is the true difference between groups. So this is going to be the basic ratio that comprises your ANOVA statistic. So we're going to obtain that ratio statistic, and we're going to use it to evaluate whether or not our IV has an effect. So this is what we call our F ratio, or your F statistic. The F is the obtained statistic of your analysis of variance. This is akin to your obtained T or your obtained R from your Pearson correlation. F is what we're going to be computing here. So the F is calculated by calculating the ratio of mean square between to mean square within. Because what this breaks down to is a obtained statistic that partitions out variance from the sources you don't care about, right? You don't care about the error variance due to the individual differences within groups, and you don't care about the error variance due to just fluctuating means when you're randomly sampling different groups. We want a statistic that partitions all of that variance we don't care about out and gives us a statistic representing the amount of variance we truly do care about. Okay, so again, if there's no effect of our independent variable, meaning that the groups are not different from one another, your F statistic's going to be 1. If there is some effect, some true effect, whereby some of the variance overall is driven by these genuine group differences, your F statistic will be greater than 1. So anytime your obtained F is greater than 1, it indicates that there may be an effect. Now, we're not getting to statistical significance evaluation just yet. But in theory, anytime you have an F statistic that's greater than 1, there might be an effect. So this is how you test for group differences in your ANOVA. You calculate your obtained F statistic and you compare it to your sampling distribution, just as we've done before. The F distribution, the sampling distribution that underlies the analysis of variance, it looks a little bit different from some other sampling distributions we've seen that, for example, are symmetrical in shape. The F distribution is actually a little bit skewed. So as with sampling distributions we've seen in the past, these are basically the probability distributions that underlie our statistical significance tests. So they're the probability distributions that depict essentially all of those critical statistical value tables we've seen before. The way these have been mathematically derived is by repeatedly drawing certain numbers of samples with certain sample sizes and various numbers of levels within your independent variable, and seeing the natural distribution of F statistics that results. Okay, so some interesting distinctions that make the F distribution look a little bit different than we've seen before is, for example, its positive skew. Another one is that the F statistic is always positive. Again, it's a ratio of sources of variance. It's impossible to get a negative F value because it's representing a ratio. So amount of variance out of 100% of total variance, right? It can only range from 0 to 100%. So your F statistic is always positive. If you ever get a negative F, you did something wrong. The mean of the F statistic is 1. As I mentioned, if you have an F that's greater than 1, it indicates that there might be an effect. Any obtained F that is 1 or lower indicates that there's certainly no effect of your independent variable. So that creates this skewed distribution with a mean of 1. And the variance or the shape of this probability distribution is going to be determined, as we've seen before, by degrees of freedom as opposed to just sample size. The way you determine what your critical value for an F statistic is going to be derived from your degrees of freedom for this analysis of variance, and the degrees of freedom are going to account for the fact that there's these different sources of variance. So there's going to be a degrees of freedom for your mean square within and a separate one for mean squares between. So given that there's two sources of variance at least, there's degrees of freedom for your two sources of variance as well. All right, so now we're hurtling towards computation. Okay, this would be some example data that adheres to the example that I set forth earlier, right? You take a series of 5 individuals at your 3 different time periods, and you get their mean level of stress. Again, the data depicts the 5 stress scores within each group, so you need to be able to see your data broken down by level. So your data would look something like this. So we're going to need a fair bit of background work before we're ready to actually compute our obtained F. There's a fair amount of computation that goes into this one, so gird your loins. Okay, we're going to need to create what we call a summary table for the ANOVA. There's going to be a summary table that guides you through the various computations that you need to do to gear yourself towards the actual computation of your F statistic. So the way you're going to get to your final F statistic takes a few steps before you get there. First, you're going to need what we call sum of squares. This is going to be a way that we capture and quantify the amount of variance from your two different sources. So you're going to need to calculate your sum of squares between groups and your sum of squares within groups. From there, you're going to need to take into account your degrees of freedom from these two different sources. From there, you're going to create those mean square terms I've mentioned before. And then, as I mentioned, the final F statistic is the ratio of MS between to MS within. So how do you get all these pieces? You're going to need to compute the following. Okay, to start, you're going to need to sum the scores for each group separately. So we're going to call this T for total sub K, meaning the total for all of your groups individually. Okay, so for example, you just add up all the scores from group 1. You then add up all the scores for group 2. You add up the scores for group 3. Okay, so T stands for total, and that subscript is going to denote which group you need the total for. So you're going to need the sum of the scores for all of your groups separately. You're going to also need the sum of all the squared scores for each group. Okay, so that piece you see there, that sigma x sub k squared, okay, this is going to be the sum of all the squared scores for each group. Again, the notation, you just need to look at it, take a breath, and realize that you know what you're being directed to do. The only new thing there is that sub k notation, which, as you now know, stands in to identify all of your groups separately. Okay, so to create your squared scores for group 1, right, you have to square each of your scores from group 1 and then add up those squared scores, so on and so forth for all of your remaining groups. You're additionally going to need to sum up all of the scores in the experiment overall, regardless of group. We're going to call this G, meaning grand total. So this is just the sum of all of your scores individually, or the sum of all of your total scores individually. Either way, this G means the sum of every single individual score in your data set. Likewise, you're going to need the sum of all the squared scores. So you squared all of the scores on the previous page, and you totaled them within the groups. Well, then you can just take those 3 squared scores from the 3 distinct groups and add those together for the sum of all the squared scores. Again, that notation, that sigma x squared, again, you should be able to look at that and understand what you're being directed to do. It's squaring, in this case, all of the scores in the data set and summing all of the squared scores. Again, recall that that sigma x squared, you do an exponent first. That means every score in the data set needs to be squared and then needs to be summed up. Okay, so this gets us going, right? We've got our grand total, the sum of all individual scores in the data set, so the sum of all 15 of those scores. We know there's an n overall of 15 and that there's 3 groups. We also have the totals within the groups separately, and we know the sample size within the 3 groups separately. We also have the squared scores in the groups separately and the overall squared scores. Okay, what do we do next? With that information, we can now calculate sum of squares total. So this is the formula for sum of squares total. This would be what I give you on a equation worksheet on an exam. Again, the idea is that barring that G for grand total, this is notation you've seen before, so you just need to look at it and understand what you're being directed to do on your data set. Okay, so you compute your sum of squares total. Got that? Amazing. Okay, then we want to calculate our sum of squares between. Again, this looks a little bit tricky because it's got that T sub k notation, it's got that G notation, but if you've been following along, the idea is you should be able to break down what this is describing and what this is directing you to do. So your sum of squares between, even though that notation looked a little bit confusing, this is what it breaks down to. All right? It's squaring your total scores, dividing them by the sample size within the group separately, doing that for all 3 of your groups, and then adding those together, and then subtracting out your grand total squared over n. Okay, so again, that equation for sum of squares between might look tricky, but you now know what all of that means, and this is what the math would actually pan out to looking like. So then lastly, we're going to need that sum of squares within. If you've been following along with the logic of the ANOVA, the idea is that if sum of squares is quantifying variance, and we know that there's different sources of variance, sum of squares within can easily be computed once you have sum of squares total and sum of squares between. Okay, sum of squares total represents overall 100% of the variance. We know that in a one-way ANOVA, the sources of total variance is from that within variance and from that between variance. So if we start off with our sum of squares total and we partition out sum of squares between, we know what we're left with is sum of squares within. So this would be how you then calculate your sum of squares within. So now we have that first column of the ANOVA summary table completed. Okay, you need your sum of squares between, within, and total. So then we just need to work our way from left to right across the table. So this is what your various degrees of freedom are for your between, within, and total. So degrees of freedom for your between groups is going to be k minus 1 or number of levels minus 1. Like I mentioned, a one-way ANOVA is when you have a single independent variable with at least 3 groups. You're not limited to that many groups. You could have a one-way ANOVA research setup where maybe you have 4 conditions. Let's say in the example that I've been using, you have people measured at vacation, people who are measured during the middle of the semester, people who have a measurement from right before finals week, and then right after finals week. Right? That would be 4 different groups. Okay? Sky's the limit. You can have as many levels as you want. Most of the time, the examples you're going to be seeing of this, it's going to be 3 groups. Okay? But the formula for degrees of freedom between in this case, k minus 1, or number of levels minus 1. So your degrees of freedom for this example is 2. Your degrees of freedom within is going to be n minus k. Overall n, so 15 in this case, representing all 15 participants in the data set, minus 3, standing for the number of groups. Okay? So degrees of freedom within is 12. You can calculate your degrees of freedom total. You're really not going to need it. Degrees of freedom between and within are more important. Okay? So then to calculate your obtained F statistic, you need your mean square between and mean square within. Well, like I said, you just work your way left to right throughout the table. Mean square between is the ratio of sum of squares between to degrees of freedom between. Okay, so you move your way across that between row. Likewise for mean square within. It's the sum of squares within over degrees of freedom within. So you're working your way left to right across this table. So now we have MS between and MS within. We can finally calculate our F statistic. Okay, so this is your obtained statistic that you're going to evaluate for significance. The larger the F statistic, the more your groups are different. Like I said, a F statistic of 1 would indicate no difference between groups, essentially. So the greater than 1, the better. Again, an F statistic cannot be negative because it's inherently a ratio. And the higher it is than 1, the more your groups are different, the more likely it is that you've achieved significance. So this would overall be your completed ANOVA summary table. This is what you're going to see in your SPSS output, so it's good to familiarize yourself with the way it's set up. Additionally, on an exam, I would likely give you a blank ANOVA summary table to help guide you through the sequence of steps. Okay, so the fact that f was greater than 1 suggests that there was an effect of the independent variable, and we like that. It also looks pretty massively greater than 1, so that's a good thing, but we want to evaluate it for significance. As usual, this hypothesis testing process is by ascertaining the chance of obtaining an F statistic that large by chance alone. So your basic comparing of the obtained statistic to the critical statistic. Your F table, you're going to need to navigate by using the degrees of freedom that you calculated just a second ago. Okay, so this is your basic critical F table. You just need to know your degrees of freedom between and your degrees of freedom within. This entire table depicts p equals 0.05, so you don't need to mess with figuring out your different critical probability levels. You don't need to mess with one-tailed or two-tailed, right? This entire table represents p equals 0.05. So you just need to navigate to your critical F by using degrees of freedom between and degrees of freedom within, right? So you had your degrees of freedom between and within, and you just find where that column and where that row meets, finding your critical F value. So as usual, you take your critical F value and you evaluate whether or not it exceeds the critical F. Does the obtained F, rather, exceed the critical F? And if so, we can reject the null hypothesis. In this case, clearly, yes, we have exceeded by a pretty impressive margin the critical F statistic, meaning we can reject the null hypothesis. What this means is that there was a significant effect of the independent variable. What that tells you is that at least one of the group means was different. Now you might be saying to yourself, which one of the groups was different? Were they all different? Was only one different? How different were they? That's what we're going to get into in the next round of lectures. All that a critical F result tells you is that at least one of the groups was different. So now I'll quickly show you how you would evaluate this same analysis in SPSS. Okay, so what you need to do is you need to set up your data set to accommodate this data. Again, keep in mind that you've got your two different variables, right? Your IV representing your condition variable, so that being a categorical variable, you would want to label in SPSS. And then you've got your stress variable indicating your participant's level of stress. And then your data would look like this, right? You have to denote your participants in each of your three conditions, right? So that first 5 rows represent the 5 individuals in the vacation condition, the next 5 denoted with the 2 are in the semester, and the 5 with the 3 were in the exam group. And then the column with stress was just their stress outcome. So you go to compare means in the drop-down menu, and you go all the way to one-way ANOVA. The independent variable should be down in the factor box. So all of the variables in your data set will initially appear over on the left. In that box there, you need to click on your independent variable and click it down into that bottom box listing factor. And then whatever your outcome is, you click that over into the dependent list. In the options, you're going to want to click at least descriptives and homogeneity of variance test. So just your basic ANOVA before we get into our post hoc tests for next time. This is basically all you need to do at this point. Okay, so then this would be your output. Critically at the bottom, you see your ANOVA summary table. So all that same information that we just computed. So you can see all of the same analyses that we just did, getting us to our F-statistic. Your sum of squares, your degrees of freedom, your mean square, up into your obtained F-statistic. Okay, so that's how you do your basic one-way ANOVA. Again, I will note, as always, that a significance level in SPSS that says 0.000, that is not actually p equaling 0. Recall how I always harp on the point that there is no such thing as a p-value of 0, because there is literally always a chance you could be mistaken. That is SPSS telling you that your actual p-value is less than 0.001. So never write that your p is 0. It is theoretically impossible. Okay, so to try and reinforce some of your knowledge on ANOVA and how it's used, I would invite you to take some time to search for an article that uses a one-way ANOVA, keeping your PsycInfo searching skills sharp. If you find a paper with an analysis of variance, make sure that you can identify what is the independent variable and all the levels, and the dependent variable. The notes that you would want to take would include what your different variables are, what was their F-statistic, was it significant. So I encourage you to do this activity to try and make sure that you've been exposed to some ANOVA research and that you understand it a little bit better. Get on a chat with some of your classmates and compare notes about what you found, because that just helps reinforce what this analysis is about and how it's written up. So I'm going to leave it there for now. I hope you guys are doing well, and I'll talk to you soon.